Good morning, everybody. Today, I'm covering some of the topics that is light source materials, quantum efficiency, and LED power, advantages and disadvantages of LED, and also comparison of light emitting diodes. Once again, the recommended readings are Gerdkaiser and John Senior book. Light source materials. Here, the importance of light source materials we have to consider. We have to select appropriate light source materials. There are two types of emissions. One is spontaneous emission that we can see in LED, and in laser diode, that is stimulus emission. The spontaneous emission due to carrier recombination is called electroluminescence. So this is a very sophisticated technology. The electroluminescence means there is a conversion of energy from electrical to light. The difference between ordinary light and this optical light is that optical LED is that it is a very minute, very tiny. The energy conversion is same as the conventional one, and the power handling capacity of this LED very less. It requires less power, and here to encourage electroluminescence, it is necessary to select a appropriate semiconductor material. We have to choose a optimum material, effective material. There are many materials which are available, out of which either we have to select elemental semiconductor or compound semiconductor. The semiconductors depending on energy band gap. Every semiconductor, either it is elemental semiconductor or compound semiconductor, and here we are giving importance for compound semiconductor. Compound semiconductors such as gallium arsenide, indium phosphide, cadmium telluride, many things are there. And here the band gap energy of that those semiconductors are very important. And these can be categorized in different way also. You can see the categories. The categories are the direct band gap semiconductors, second one indirect band gap semiconductors, and some commonly used band gap semiconductors are shown in the following table. You can see the table. The first column shows that semiconductor material, and here the combination of materials are used, and second one energy band gap for that, and third one recombination rate. The first example, gallium arsenide, it's a compound semiconductor made up of gallium and arsenic material, and here it is direct. The band gap that is 1.43. The recombination rate 7.21 into 10 to the power of minus 10. Similarly, GaSp, gallium, selenium, and that's a direct band gap energy 0.73, and recombination rate that is 2.39 into 10 to the power of minus 10. And third one, indium arsenide, direct band gap energy that is 0.35, and the recombination rate 8.5 into 10 to the power minus 11. Further continuing this one, and if you see that one more material that is elemental semiconductors, silicon, and it is indirect band gap energy that is 1.12, whereas recombination rate that is 1.79. And INSB also, that is a direct band gap energy that is 1.18, and recombination rate 4.58 into 10 to the power of minus 11. Then another elemental semiconductor, germanium, indirect band gap energy 0.67, and recombination rate 5.25 into 10 to the power of minus 14. And one more material that is a compound material, gallium phosphide, indirect band gap energy 2.26, and recombination rate 5.37 into 10 to the power of minus 14. Now, With this knowledge, we can understand the how to select the light source material. One should be very choosy and selective when you are fabricating LEDs and laser diodes also. Direct bandgap semiconductors are most useful for this purpose. I have given 7 examples, out of which direct bandgap and semiconductors are preferable. Indirect bandgap semiconductors, the electrons and holes on either side of the bandgap have same value of crystal momentum. So that is the problem. That's what we prefer direct bandgap semiconductors. Hence, direct recombination is possible because the recombination occurs within a fraction of a microsecond and several nanoseconds. Now, the direct bandgap materials and indirect bandgap materials, if you consider, in indirect bandgap semiconductors, the maximum and minimum energies occur at different values of crystal momentum. So this you can select any material, but it must be the crystal momentum is very important, and the band gap energy that is to be maintained, and the electron hole recombination occurring, the rate of occurring, that is also much important, and each electron hole recombination which gives one photon. The number of photons liberated for each and every electron hole recombination, there must be some equation, and the maximum energy, maximum that is a photon energy that must be liberated, for that all electron hole which are recombining, that must be fruitful. The recombination in these semiconductors is quite slow in some of the materials, and that is also 10 to the power of minus 2, very less, and sometimes 10 to the power minus 3 second, very less. The active layer semiconductor materials must have a direct bandgap energy. That's what we prefer these things. In direct bandgap semiconductors, electrons and holes can recombine directly without need of third particle to conserve momentum. The crystal momentum, to reach that crystal momentum, we have to use direct bandgap semiconductors. In these materials, the optical radiation is sufficiently high. Here, optical radiation, that's a liberation of this one, when electron and holes, when they are recombining, and photons are liberated, and for that optical radiation, it must be sufficiently high, then only photons will be liberated. These materials are compounds of group 3 elements. So there are group 3 and group 5 elements. Group 3 elements we prefer here. Group 3 elements, if you consider aluminum, gallium and indium, and similarly group 5 elements, phosphorus and arsenic material and Sp material also. And in addition to that, there are ternary alloys are used. Alloys are a mixture of these things, that is gallium, aluminum and arsenic we can use. And here emission spectrum of one of the combination, if you consider gallium, that is 1 nsec, aluminum X, and X is the proportion, that is certain content, and LED, that is one of the example which is shown. It is an example, and you can see that, and this is the emission spectrum. This is an example, experimental details we are giving, and gallium 1 nsec, aluminum X, and arsenic LED, which is emitting photons by means of electron hole recombination. And here in this graphical representation, output power which is given on the y-axis, and wavelength in nanometer which is given on the x-axis. If you see this particular spectrum, and there is a peak wavelength, and it is emitting at the peak wavelength, the emission energy or power, that is maximum at 810, and below which it is increasing in manner, above which that is decreasing in manner. That is said to be peak wavelength. And one more parameter also we are mentioning here, that is half power beam width, like that. And here the, because LED which produces a wider spectrum which is undesirable, and it loses its energy very much quickly, but laser diode which is having narrow beam width, narrow spectrum, we can say narrow spectrum, and radiation power that is highly intense, highly directional, monochromatic. But LED doesn't have that much intense beam, and you can see it has 36 nanometer. That is apart from that peak wavelength, 18 nanometer left side and 18 nanometer right side, put together 36 nanometer, and it is much wider, and that means it's a spectral which is maximum, and this can be used for some of the application. This is the emission spectrum of the particular combination. Next, there are some other mathematical expressions. I want to highlight this one, and here lambda is the wavelength, and that is nothing but Hc by E. The peak output power is obtained at 810 nanometer. That is shown in the emission spectrum. The width of the emission spectrum, that is a half power, that is a 0.5. 0.5 is nothing but 3 dB power. It is referred as full width half maximum. FWHM spectral width, and for, as I mentioned, for LED it is broader, for LED that is very less, and for the given LED FWHM, that is nothing but full width half maximum, that is 36 nanometer, 18 plus 18. The fundamental quantum mechanical relationship between gap energy E and frequency V, optical frequency, we call this one as optical frequency, that is given in the emission spectrum. Next, always we mention this wavelength in terms of micrometer or nanometer. That is equation that is equal to 1.24, and Eg in terms of electron volts, where energy E is in joules and wavelength lambda that is in meters or micrometers or nanometers, and expressing the gap energy Eg in electron volts and wavelength lambda in micrometers. Even we can mention in terms of nanometer for this application. Different materials and alloys have different band gap energies, and I given only one example here, and if we can change x parameter, y parameter, and different combinations also we can use, and which exhibits different patterns, emission patterns, etc. Next, if you see this equation for the light source material, Eg is equal to 1.424 plus 1.266x plus 0.266x square. Similarly, this can be mentioned in terms of y also, that is Eg is equal to band gap energy 1.35 minus 0.72y plus 0.12y square. That means here the band gap energy Eg can be controlled by two compositional parameters, and here x is one of the compositional parameter and y is another compositional parameter within direct band gap region. The quaternary alloy, that is indium 1 minus x, gallium x, and As y, and P1 minus 5 is the principal material which is used in LED. Scientists they thought about all these combinations, and the compositional parameters x and y also they are changed. By after changing all these things, they fabricated LED, and which produces very good beam, and which is having narrow spectral width and bit intense also. And two expressions relating Eg and x5 are given in the above equation. Now, one more very important topic that I would like to highlight, that is quantum efficiency and LED power. And every device and it has certain efficiency. We see the device is efficient when it is producing highest output power. Here we compare output power by input power applied, and output power, that is nothing but photons which are liberated or generated, and input power, that is the electron hole recombination which is taking place. Now we follow certain formula here, that is the internal efficiency of LED. First let me complete internal efficiency of LED, and that is R2 by R2 plus Rn2. That is the internal quantum efficiency, that is defined as the ratio of radiative recombination rate to the total recombination rate. We sum these two, and that is the total recombination rate, where RR is radiative recombination rate and RNR is non-radiative recombination rate. Now, continuing further, and you can see that that is N by RR, that is nothing but 2R. Similarly, N by RNR, that is nothing but 2NR. That is, if N is excess carriers, then radiative lifetime is given in first equation, that is a radiative lifetime. It is radiative, that is a pertaining radiation. And the non-radiative lifetime is given in the second equation, that is RNR and 2NR, that is given, clearly it is given. Next, simplifying further, the internal efficiency can be simplified like this, that is 1 upon 1 plus RNR by RR. That is next, if you consider this internal efficiency that can be mentioned in terms of 2R and 2NR, that equation represents that one. The internal quantum efficiency which is shown in the above equation. Next, this can be simplified in the further way, that is 1 by 2, that is equal to 1 by 2R plus 1 by 2NR. The internal efficiency after simplification, that is 2 by 2R. The recombination time of carriers in active region, that is tau, it is also known as bulk recombination lifetime. That is the first equation which is written. Therefore, the internal quantum efficiency which is also mentioned, that is 2 by 2R, that is the second equation. You can go through that. Next, continuing further, RR can be almost, that is RNR, that can be written 1 by Q. Q is the charge of an electron, and the internal efficiency, that is RR by 1 by Q. 1 by Q you can say, then RR is equal to internal efficiency of the LED into 1 by Q. If the current injected into the LED, that is said to be I, because here the current is very, very important. It varies the number of electrons also. Q is the electron charge, then total number of recombination per second is given in the above expressions. Next, simplifying further, and here the internal efficiency, that is equal to RR into HV, the that is internal power, and internal power is equal to efficiency, quantum efficiency into 1 by Q into HV, and thereafter after simplifying, internal efficiency into 1 by Q into H into C by lambda, then thereafter after simplification, and that is internal efficiency into HCI by Q lambda, that is nothing but internal power. And here let me differentiate internal power generated by the LED and external power available from the LED. So there is some difference that also we have to calculate. And here the optical power generated internally in LED, it is clearly mentioned in the equation. Now, continuing further, and here not all internally generated photons will available from output of device. There is some difference between internal power and external power. The external quantum efficiency is used to calculate the emitted power. So some amount of photons will be lost. Photons are generated inside, but when you are collecting outside, some amount will be lost. That is due to some coupling loss or some other loss, maybe some other loss. The external quantum efficiency is defined as the ratio of photons emitted from LED to the number of photons generated internally. So there is a difference. We have to equalize this one. To equalize this, a good design is required, good fabrication is required, good scientists, they have to think in such a way that it must be almost equivalent to 100%. 100% in practical it is impossible, and it is in all devices which are not completely efficient, and we may expect some 90%, 95% or even less than that. It depends upon the design, fabrication, etc. And it is given in the following equation. Now see this equation here, the external efficiency, quantum efficiency, that is equal to 1 upon n into n plus 1 square, and the optical output power emitted from LED, that is given like this, that is external quantum efficiency into internal power. and P is equal to 1 by n is the excess carriers, n into n plus 1 square into P internal. This is the equation, one of the very important equation. Now, based on this problem, let me solve one example. The problem is given here. First, let me go through this problem. Later, we will find out the solution for this. The radiative and non-radiative recombination lifetimes of minority carriers in the active region of a double heterojunction LED are 60 nanoseconds and 90 nanoseconds respectively. Determine the total carrier recombination lifetime and optical power generated internally if the peak emission wavelength for the silicon, that is 870 nanometer, and the dry current is 40 milliamps. And all the details which are given here, let me read this problem and let me go through that, the given data, and afterwards we can find out a solution using the formulae. And here the given data, and you can go through the given data are lambda is equal to 870 nanometer. You can convert that one into meters, that is 0.87 into 10 to the power of minus 6 meters. And here you can see tau r, that is 60 nanoseconds, and tau nr, that is 90 nanoseconds, and injected current, that is 40 milliamps, and you can convert that one into amps, that is 0.04 amps. Now, the first point is the total carrier recombination lifetime, that is 1 by 2r minus, you can 1 by 2 is equal to 1 by 2r plus 1 by 2 nr. 1 by 2 is equal to 1 by 60 plus 1 by 90. Then after simplifying, you will get certain result. You can see that. You can calculate that. Then what is the internal optical power? Internal optical power, that can be written like this. This is the formula. Already I derived that one. P internal is equal to the quantum internal quantum efficiency HCI by Q lambda. And here this can be rewritten like this: the internal quantum efficiency tau by 2r, and HCI, and H is Planck's constant, and C is the velocity of light, and I is the injected current, and Q is the charge of an electron, and lambda, that is the wavelength of operation. Substituting these values, that is tau is 30 nanoseconds, and tau r, that is 60 nanoseconds. After calculating this, the P internal would be 34.32 milliwatts. You see the power which is consumed by the LED, that is in terms of milliwatts, very small amount, but it is sophisticated and well designed device. It requires small amount of power. Next. Now, let me cover some other topics like what are the advantages of these LEDs. I have covered two topics. That is, first is that is light source materials, and what are the different types of light source materials, and compositional parameters of those things, etc. Second one, quantum efficiency and LED power. Third one is advantages and disadvantages of LEDs. And if you take up LED for the any establishing optical link, it is very simple. Easily you can design this one, easily you can install, and ease of manufacture. There is no much problem in fabrication, uh, no problems, and easily can manufacture. Already it is well advanced, easily available also, simple technology, simple system integration compared to LD. LD is very complicated and extra care must be taken, but it's a simple system integration is sufficient, and it is low cost because it is used to the maximum, so it is less costly, and it is highly reliable optical transmitter, high reliability. The reason is that once if you fabricate and install in the link, and it can be used for 3 to 5 years effectively, thereafter also you can use, and it's so that it is said to be a high reliable device. Next, every system it has unique advantages and specific drawbacks. LED is the first optical transmitter which is fabricated and manufactured, but thereafter LD, that is investigated. LD, it is a best device, but LED also it is used for the low data rate applications and low distance applications. This can be effectively, we can use this one. And LED is preferably it is used, but it is bit costly. Now let us concentrate only on disadvantages of LED and refraction of light at semiconductor or air interface. There is a refraction. Refraction it should not happen, but there is some refraction whenever there is a gap interface. This happens, that leads to certain losses also, and we have to avoid that one. Second disadvantage: the average lifetime of a radiative recombination is only a few nanoseconds. Therefore, modulation bandwidth is limited to only few hundred megahertz. So that means data rate is very less. Though we can achieve highest data rate using LD, but as far as optical transmitter is concerned, this is not up to the mark, and easy design, easy fabrication. But this for high data rate application presently, and we are using wider bandwidth, high data rate application. For that purpose, we want LD. LED it can be used up to 200 megabits per second, not more than that, as far as digital technology is concerned. For low-end application, this can be used. A third one, low coupling efficiency. Coupling efficiency is not up to the mark. There is some interfacing problem, and all the power is not coupled to the fiber or fiber to photo detector, especially LED to fiber, and so that coupling efficiency is not up to the mark. And fourth one, low chromatic dispersion. As I mentioned, chromatic dispersion is one of the very important dispersion, and this leads to certain losses. Chromatic dispersion is also said to be material dispersion, and this is the major dispersion compared to waveguide dispersion. And in LED, if you use LED as an optical transmitter, that leads to chromatic dispersion, so that the signals will be bit distorted using this LED. Now, the last topic of this one, that is a comparison of surface emitting LED and edge emitting LED, and these are the two types of LEDs. As I mentioned, surface emitting LED, that is first it was investigated. After few years, after 5 years, edge emitting LED that was investigated. We prefer edge emitting LED, and construction wise is good. Scientists, engineers, they want that one. And let me highlight why edge emitting LED that is preferred compared to surface emitting LED. Now, in the first column, LED type is given. There are two types: surface emitting LED, and second one, edge emitting LED. In the second column, maximum modulation frequency. In the third column, output power, that is in milliwatts, and in third column, fiber coupled power, that is also in milliwatts. Now, the first one, first parameter, maximum modulation frequency, that is in megahertz. And surface emitting LED, maximum we can use up to 600 megahertz in analog communication. In digital communication, we can say that 60 megabits per second, not more than that. That's the main limitation of the surface emitting LED. Now, if we consider second type, the edge emitting LED, that is, we can go up to 200 megabits per second. This is an advantage, and multiplexing is possible, and more multiplexing is possible, and engineers, users, and scientists, they prefer edge emitting LED rather than surface emitting LED. Now, the second parameter, output power in milliwatts, and here for the surface emitting LED, it is you can say that it is maximum 4 only, 4 milliwatt. But in the edge emitting LED, power which is it can handle up to 7. It is an advantage. Output power. Power is more means distance of communication is more. That's what output power in milliwatt. That is one for surface emitting LED 4. It is discarded, and edge emitting LED, that is 7. It is preferred. The last one, fiber coupled power. This is also much important, and here maximum power can be coupled using this one, that is 0.2 milliwatts, very less. But in edge emitting LED, that is 1 milliwatt, it is 5 times more than that. So maximum power can be coupled to the fiber. This is an advantage of the edge emitting LED over surface emitting LED. With this, today I am completing these topics. Thank you.